Okay, so hello everyone, and welcome to the last hangout of this gravity course, devoted to more specifically to gravitational waves and black holes. Okay, as you learned in the course, space-time is important, and so this is an event in space-time, and so we are in space. We are at Stanford. At SLAC, exactly. We are hosted by KIPAC. And time is important as well, because this is, the time of many very important discoveries. So I think this hangout should be very exciting, especially because we have gathered very talented experts of this field. So let me first turn to Tom Abel, who is the director of KIPAC, so that he tells us a little more about space. Where are we? What is KIPAC?
Yeah, very good. So welcome. This is the Kadley Institute for Particle Astrophysics and Cosmology. That's the acronym is we just call lovingly KIPAC. We're an institute that bridges SLAC, the SLAC National Accelerator Laboratory, the Department of Energy Laboratory, with Stanford University. So we're hosted in two different buildings. We're very happy to have Pierre here as a visitor. You have to imagine there's about 120, 150 people or so engaged in the whole research that we do here that thinks broadly about some of the biggest questions we have about the universe. What is dark matter? Where is it? What is dark energy? What makes the universe accelerate so rapidly? We think a lot about high-energy astrophysics questions as well, but also study extrasolar planets, and sort of have a broad range of bringing computation, theory, observation, and real experimental work, sort of building the next-generation instruments to discover things about the universe. Those are the mission for the Institute. Here. It's a pleasure to be here.
Okay, thanks a lot. So let me go around the virtual roundtable just to introduce each of our guests, and then we'll come back to each of them for more specific questions. So Roger Blanford is next to me, is a former director and founder of KIPAC, and is world renowned expert on black holes, so that's we are very lucky to have him here to discuss black holes. But then this hangout is a little more complex. We have different locations. So George Smoot is not in Paris this time, is hosting this with me from Berkeley. So hi, George. Okay. Then Mike Landry is from Hanford Lab in LIGO. So we'll come back to Hanford Lab. Most people didn't know where Hanford was, but now this is the center of the world, or one of the two centers of the world. And finally, Stefano Vitale, who is in Trento, and who is the PI, the principal investigator, so basically the scientific head of the LISAPathfinder mission.
Hello, everybody.
Hi, Stefano. Okay, now Stefano, since you appear on the screen, let me start with you. Well, I'll just ask. I'll use my privilege of hosting this hangout to and the fact that we have experts around the table to ask my own question, and then we'll I promise we'll get to your questions. We have many interesting questions. So Stefano, what was the most intense moment? Our learners have seen you in an interview I think a few days before the launch. So now the results have been published. So could you tell us what is the most intense time moment during the mission?
Yeah, during the mission, right? Because during the development, there were many, but it would require a dedicated hangout. During the mission, obviously the launch, because all 15 years of work are in that piece of metal that is going up in the sky. You have no guarantee that you're being able to communicate to it, but everything was fine. LISAPathfinder had two launches. One is the launch of the rocket from the Earth. The other is the launch of the test masses in free fall. that was really intense and tense, and also that one went well. However, to me, the most tense and intense moment was the first time we saw the data. And as soon as we saw the data were well beyond the requirement, and that was a great moment. I mean, it was really rewarding after, as I say, 15 years of work. Oops. Okay.
Thank you. Okay, we'll return to questions about LISAPathfinder and Lisa, but let me just go around. Mike, okay, so you're the scientist in charge of detection, at Stanford Lab, and you're also affiliated to Caltech. So, could you tell us a little more about your job, and also my question would be to you. Okay, just suppose that at this moment, gravitational wave is passing, through Stanford Lab. What happens? Is there someone sitting in front of a computer suddenly saying, "Okay, here's a gravitational wave"? Could you sort of, give an idea of, what it means to see, to detect a gravitational wave in the lab?
Sure. Yeah. Thanks very much for the opportunity to tell you a little about LIGO. So I'm located at LIGO-Hanford Observatory, and there's LIGO comprises two observatories. There's the Louisiana site in the southern United States and ours, both 4-kilometer long L-shaped interferometers. And I'm the, as you said, the detection lead scientist. So that means I concentrate on aspects of detection going into observing runs. I'm worried about the states of codes and the analysis and readiness for triggers. And once we do have triggers, how we vet them, and if we have a gravitational wave candidate, in a very key and focused way, how we defend that, because with such a tiny signal, the distortion of space is such that the arms are changed in a differential way only by 1/10,000th, a few 1,000ths the size of a proton over 4 kilometers. That means you have to do a lot of work to validate any signal. So that's really what the role is. In the event, you get a trigger, and this happened several times during our initial observation run with advanced LIGO. That means you may have a gravitational wave passing through. We had 2 binary black hole events that we've reported on. We just reported on our second gravitational wave detection from a binary black hole yesterday. And the first one we announced in February. Or you could have a spurious noise trigger between the detectors. So when we're running, we're in a 24/7 operation mode. There'll definitely be an operator on site 24 hours a day, and 16 hours a day there's a consultant scientist in the control room. And then there's many people around in day and evenings as well. So if you get a trigger, then that's typically found by online codes within a minute to 3 minutes of in the case of the detection of event, within 3 minutes of the passage of this gravitational wave. And throughout the run, we were alerted. So I would get a cell phone ring, basically a text message saying, this candidate, this code, and I would get up if it was in the middle of the night and go to my computer and look at the data and join a call, a rapid response team of people, some at the sites, some who drove into the sites, some who were distant from the sites, working from their homes or home institutions, in order to vet the data kind of rapidly. Because, one, we want to know if it's a real gravitational wave candidate or if it's a spurious noise trigger, and we certainly rejected, these triggers in the middle of the night or in the day sometimes, which were just sheer noise in our interferometer. So sort of false alarms. But in the event it was a gravitational wave candidate, we wanted to have electromagnetic astronomers follow it up, because you want to do multi-messenger astronomy. You want to look with many different telescopes, electromagnetic telescopes of various bands, in order to see if you have some, electromagnetic counterpart, and learn in many different ways about the same event. That was the idea. For the very first event, though, we weren't that organized. we had the trigger. It occurred at about 2:50 in the morning here, and it was several hours by email in which we contacted. Our protocols weren't in place just 4 days before the official start of the run.
Okay, well, thank you very much. Okay, we'll return to that, of course, with the questions. Okay, so let me continue to go around. Okay, Roger, the question to you is, you're the expert on, on astrophysical black holes. It's interesting because, for a while, for a long time, when we were talking about the black holes of theorists, those in general relativity books, and then the astrophysical black holes. Now we have to reconcile the two somehow. So what was your reaction, at the time of discovery? Did you expect this? Well, probably not that early, but also as you're very familiar with black holes. So,
well, when I first heard about the event last September, on September the 14th, I was as excited as anybody. I think it was wonderful to hear about it, and when I saw the data, it was such a clean signal. That was for me a very big surprise. I think many astrophysicists expected that the neutron star binaries would be the first signals to be seen. And that wasn't because they did not think about the black hole binaries. It was just that there was less, we were less confident that those would be present. Whereas the neutron star binaries, we can see them as radio pulsars, and so we can make a much better estimate of their incidence. What has turned out is that this population of black hole binaries, which many people had thought about, and in my case, I'd certainly hoped for this because I thought this was the most exciting initial outcome from LIGO, that we would actually see the black hole binaries. That was still a great surprise when it happened, and it's wonderful. And we've got this large population, and then in the course of time, I fully expect that we will see also the neutron star binaries as well. So we're going to learn a lot about astrophysics, and we've already learned a lot that's very encouraging about the general theory of relativity.
Okay, so again, we'll return to all this because that's the main topic of this hangout. Okay, let me. Okay, we just had a slight problem with. Hopefully, nobody lost the image. We did. Okay, so let me return to Tom for a second. Tom is an expert on simulations, big simulations, and during the course we have seen some of the simulations, maybe actually some of yours we've been using. Recently there was an open house at at KIPAC, and there were some absolutely marvelous 3D simulations. So we should actually try to give you some links to some of Tom's simulations because they are absolutely extraordinary. So why does one need, apart from the spectacular effect, but why do scientists need to have three-dimensional simulations, and how do you use three-dimensional simulations?
Simulations for us are like the laboratory, right? So we're always in this business, like in this particular case, we're talking about throwing black holes at each other is very expensive and very dangerous. We wouldn't even know how to do it in the laboratory. But on a computer, we can try these things out. And sort of particularly, we're, in many of these cases, there's a lot of physical effects that come together. Gravity is pulling gases together. The gas itself, as it's changing temperature and density, it changes its makeup, its composition. Many extra effects of magnetic fields play a role. You have relativistic particles that have an impact of how things move around. And there's very few things that we can do with pencil and paper to work out all the effects and how they play together. So the computer becomes really our laboratory. And in many cases, actually, what we're trying to do is gain intuition. So, what happens if we have very massive stars that blow up in supernovae, or they don't? How do we contrast that? In a computer, we can try out different versions of this virtual universe, and then from that get an intuition which part of the physics is most important for explaining some of the things we do observe. And so for me personally, I spent a lot of time trying to think out, what are the very first things in the universe. And so we had to write all this computer code that can follow all the gas as gravity pulls it together in some very small region of space to eventually make a star. And we found they became all very massive stars. And most excitingly for us, it was like in 1 out of 5 cases, we always got massive binaries. And so when I first heard about the LIGO announcement, I was like, oh my gosh, this could be very interesting. Wouldn't that be amazing if we were that lucky that the black holes we can see now and they're in spiral actually were some of the very first stars that formed in the universe. So these will be very indirect, right? We wouldn't see those stars throughout cosmic time and see that evolution. But on a computer, we can try out many of these ideas and sort of weigh, okay, what is the most likely explanation of a given phenomenon? So I think that's a bit the excitement of bringing all these different parts of physics, the computer science, the parallel programming, the large supercomputers that we use for it. There's many of aspects. You have to learn quite a bit about a lot of things, and that's the excitement of doing that type of research.
Okay, thank you. Okay, I promise I won't, ask all my questions. I'll come to your questions because that's, what the hangout is for. But I'll not resist, asking my own. Okay, so let us start with question on LISAPathfinder and LISA, because I know that Stefano, it's late in Europe. Stefano came specially to the lab to get a good connection, and so he might be dropping off the hangout before the end. Well, anyways, thanks Stefano for staying late in the lab.
Sure.
Okay, so we have one question from Martin about LISAPathfinder and exactly what is LISAPathfinder doing. And the question is with the discoveries of black hole collidings to form gravitational waves. What will be the next phase? So maybe you could recall to everyone, remind us, what LISAPathfinder was testing and what is not tested, and what
absolutely.
will be the role of LISA to do.
Okay, so LISAPathfinder, we describe it usually saying is one of the LISA arms squeezed from a few million kilometers to 30 centimeters and put in a spacecraft. And what it needs to demonstrate, or needed to demonstrate, and has demonstrated, is that this 2 test masses that have to be very, very quiet because only the gravitational wave should move them. In reality, they are very quiet, so that we are able to do the disturbances so low that they stay basically in a certain frequency ranges, the stillest thing in the universe, I think, or something like that. If we can demonstrate that, that's the only thing in LISA that you cannot really demonstrate on ground, because 1g, the force of gravity of the Earth, is a killer, and making a significant test on the Earth, it turns to be impossible. What is missing, obviously, in LISA is the 1 million kilometer measurement of the motion of the spacecraft, right? Because in LISA, the idea is that you measure the 2 test mass relative to the spacecraft among them, and so in reality, you're measuring the motion of the 2 test masses due to the gravitational wave. The spacecraft-to-spacecraft link, we have not tested. We didn't have the 1 million kilometer. It had been a bit expensive to have the 1 million kilometer. However, we know that all that can be tested and demonstrated and developed on ground. 1G has very little effect, and so that's the next step. The next step is to start developing that part, with actually the work in ESA and in NASA has gone over for years, and now ESA is investing quite extensively on that. And the next step is basically LISA. And we learned recently that ESA intend to move on LISA or whatever is called the gravitational wave observatory with no discontinuity to LISAPathfinder. So the first step toward the development of LISA will start now at the end of this year. So for us, we're counting on a little rest. I don't think we will get any. And then there might be some decision to be taken, but a bit later in the time on where are the priorities, who goes first. But basically, the work on the gravitational wave observatory will continue just after Pathfinder. And obviously, you know, gravitational wave observatory in space is low frequency, so it's very deep field, huge sources, because these are slow sources and show up only low frequency, but that's another argument, right? That's what LISA is going to do.
Yeah, so we have some precise questions about LISA. So maybe since you're one of the people in charge of the LISA mission as well, the next stage. Let's get to those. For example, there is one from Anne who is asking, are the masses, so LISA has got 3 satellites, it makes a triangle, and so there are test masses at the center of these satellites. And she's asking whether the masses are at an exact constant distance from one another, and how do we measure then the fluctuations? So maybe you could answer
no, they are not at a constant distance. They basically all the constellation breadths over the year with the frequency of the year, and it breadths by many thousand kilometers. But we measure the motion at certain frequency. This is very slow, appear in the data like a drift, while we are interested in this oscillation like LIGO, only, what is that, 1 million times slower. I mean, instead of oscillating a few times per second, here we are talking waves that are oscillating in a few hours to a few minutes. Still, a few hours is not a year, right? And this large breading of the arm length happens over the year, so we can distinguish. You will see this large motion, and then when the gravitational wave comes, you see a quick thing superimposed to this large motion. So that's why we don't measure the distance. We measure the change in the distance, the displacement. We need to know the distance to some approximation, but it's meter, not femtometer as we do for gravitational waves.
And so precisely, in the case of LISA, you have test masses at the center of the satellite, and the satellite are sort of repositioning themselves in order to protect the mass. But in the case of LISAPathfinder, you have 2 masses. Mm-hmm. So how do you deal with that problem of having a single satellite, that sort of should accommodate the motion of 2 masses?
We deal with it carefully. Well, with a satellite, we follow one of the test masses, like in LISA. That's clean, and so we have to cope with the other one. The other one, if you could create an environment where there is no constant force, the other one will stay put, and you do your measurement. Unfortunately, it does not. We put a lot of effort in making the gravitational field on board the spacecraft flat, so that there is no difference of force between the test masses. It turns that we were even better than we thought. We have a pico-g of gravitational difference of gravitational force between the test mass. Nevertheless, we have to compensate this pico-g, and we give a very small electrical force, a pico-g of electrical force, at very, very low frequency. So the test mass is free in some frequency range. At the lowest frequency is compensated. That makes a little noise, and you have to correct for this effect. But basically, we were expecting this to be the dominating noise in the system, but the gravitational balance of the satellite was so good that it wasn't. We are dominated by thermal noise, by molecules hitting the test masses and shaking them around.
So in order that everyone understand what the pico G is, it's 10 to minus 12 times the acceleration in the Earth gravity field.
Pico is a thousandth of a billionth of the gravity on the Earth. The disturbances we measure are femto G, sub-femto G, and if you want to know what a sub-femto G force on the test mass is the weight of a bacteria in your hand. If somebody put a bacteria in your hand, that weight is a femto G. Actually, it's a femto Newton. That's so small. And in reality, the mission was supposed to be picometer and femto G. It turns to be femtometer and femto G. It's a femto mission. Right? We call it femto mission.
Okay.
A femto, by the way, a femto is 1/1,000,000th of a billionth. Right?
Yes, I admire you how fast you can translate. I have to write the number of zeros and to count the number of zeros to say this kind of things. We have a funny question from Paul about LISA. We know that rotating systems are emitting gravitational waves. So LISA is a rotating system. So it should emit gravitational waves. So is this is this a background to the signal that LISA itself is measuring?
Our life would be much easier if gravitational wave emitted by small bodies were so intense. Gravitational wave would be a thing of the past, would have been observed centuries ago. Unfortunately, the mass of the LISA satellite compared to the mass of the sun or a black hole or a supermassive black hole is nothing, right? So yes, it emits gravitational wave, but beyond orders and orders and orders of magnitude beyond what could be detected by LISA itself.
But on the other hand, as you stressed, you're very sensitive to the gravitational attraction of the matter which is inside the satellite. Isn't that right?
Oh yeah, but that's the static force. I mean, the much more competent colleagues that are in the room will forgive me. Here you're measuring the tide that the distant body is producing on you, and that's very, very tiny, right? That's what a gravitational wave detector detects, is the propagating tide, and the tide, even the tide of the sun, is so weak compared to the force of the sun on the Earth, right? The effect of the tide of the sun on the shape of the Earth is minute compared to setting the Earth in orbit around the sun. So there is a huge factor in between.
Okay, and so what are the next stages for LISAPathfinder now that you've published?
LISAPathfinder is an interesting object. It's a laboratory at 1,000,000 kilometers from us. And honestly, these days, the only difference between a laboratory in your building and one at 1,000,000 kilometers is that you cannot send students to the lab. That's the only difference, because all the rest is done in remote. You notice that the laboratory is not in the basement because it takes 10 seconds for the command to go up to the satellite and go back. But I think it's a fair description of LISAPathfinder that it's a physics laboratory operated in remote, because what we are doing is a series of experiments now to understand the disturbance we see, the residual very small acceleration we measure between the test masses by what are generated, right? Magnetic force, electric force, collision with molecules, collision with photons. There is a wealth of effect. Our error budget is a book of 40 pages, right? 99% is negligible, but we have to think about before we decide that was negligible. So the rest of the mission, which likely be extended till the end of May or next year, is a series of dedicated physics investigation to investigate all the force disturbances on the test masses. Some we have already run, some need to be run again.
Okay, well, thank you. So let's move to black holes and the recent announcement from LIGO. We have one question from Jean, and I guess that's for Mike. How do scientists know which direction the gravitational waves are coming from?
So gravitational waves is distortions in space. They're not sound, but they act like sound. And so you have 2 ears, and the way you actually register where a sound is coming from, coarsely, is based on the time of arrival of the sound from one, as it passes through one ear and into the other. And so with that, your brain makes a quick calculation that the sound is coming from over there, or over there. It's not a very good positioning system, not like your eyes, which is an excellent positioning system. So a gravitational wave detector works the same way. One detector doesn't have any ability to locate position in the sky. But if you have multiple detectors, 3 minimally, you can triangulate a location in the sky of a gravitational wave source based on the time of arrival. As that plane wave races at the speed of light through the Earth, it's going to register in one detector, then the other, and then the other. So with 3, you can triangulate. Better still would be 5, so you can make the error box, that position in the sky, smaller and smaller, and that facilitates the follow-up by electromagnetic astronomers. They'll be able to search smaller regions of the sky more thoroughly if we hand off smaller error boxes in the sky. So that's the way it's done. Currently, the 2 LIGO detections, LIGO-Virgo detections with the LIGO interferometers, only make use of 2 detectors. So you can't localize very well. You might think, well, you'd get an annulus in the sky for 2 detectors, but the 2 detectors reside on the continent of the US, and there's some Earth curvature to that. So we're a little more sensitive to the different polarizations of the gravitational waves as they arrive at the Earth, and that allows you to make it not an annulus in the sky, but error boxes, something on the order of 900 square degrees. So when we hand off a sky localization right now, it's with a big, big error bar. We need Virgo to come online. That will happen late this year or early next year. They'll join in our observation runs. After that, Kagra in Japan in a few years. After that, still 2022, 23 would be LIGO India, and that will allow this sky localization to shrink.
So let me ask the same question with LISA, because in the case of LISA, you have only 1 detector.
Yeah, however, for many sources, the waves are slow, and LISA rotates in the wave, and so in a sense, there's many detectors, right, in time, and this allows to locate the source. For the most intense source, we're talking an arc minute, right? For a binary supermassive black hole binary collapse, the most intense one, I think we are talking of an arc minute. It's not very different from what you do on ground, but here, I mean, you take advantage of the fact that the wave are somehow long-lived, so that the detector rotates. And LISA also is not just 1 interferometer. You may think as a sort of 2 semi-independent interferometer, because every 2 arms of the triangle form an interferometer. And so also this as a consequence in locating the source and measuring independently the polarization.
Okay, we have a certain number of questions about the spin of black holes. So maybe the first question is from Anna. Exactly, what is the spin? If a black hole has a spin, what exactly rotates? The horizon, the singularity, and does it change or add any physical properties? What's the difference between spinning and non-spinning black holes? Okay, clearly this is a question for Roger.
Okay, thank you, Pierre. Yes, black holes can indeed spin. In fact, the sort of black holes we think we're looking at in the universe in astrophysics are characterized by their mass and their spin. Now, as I expect many people know, a black hole has an event horizon, and that event horizon is, if you like, the surface or point of no return beyond which you cannot, by classical processes, re-emerge from the black hole. Now, that event horizon is, in a sense, a smooth surface, so it's unlike looking at the surface of the Earth from outside of it and seeing Paris go by, for example, every 24 hours and deducing that the Earth was spinning. There's no sort of mark on the surface or the event horizon of a black hole. But what the black hole does do is it drags the space-time around with it. And this has a rather fancy description. It's called the dragging of inertial frames. And this phenomenon, the dragging of space-time around with the black hole, requires that, if you like, in a thought experiment, a satellite that was just orbiting outside the black hole would have to move with the direction of the black hole. We couldn't make it by a series of ropes and pulleys or whatever, stay at rest outside the black hole. It would have to move around with the black hole. So that, in a thought experiment, is a phenomenon that follows from the spin of the black hole. If we talk about what actually happens in the nuclei of galaxies or in binary stars with black holes in them, then the consequences of this dragging of inertial frames are that gas can orbit closer to the surface of a black hole when it is spinning, and we can actually observe the consequences of that, especially using X-ray telescopes. And another major consequence is that when a black hole is spinning, it has a certain amount of energy associated with that spin, and that energy can be tapped by magnetic fields and electric fields, and that energy can be used to power the giant radio jets and relativistic jets that are observed with these black holes. So we have two consequences, if you like, that have both been observed. One is the jets associated with black holes, and the other is the properties of the disks of gas that orbit them. And so that's really how we, in practice, see the spin of the black hole.
And Paul is also interested in black hole spin, and is asking, there is a maximal rotational velocity, maximum spin. So how can we understand this?
Well, I think this is a very interesting prediction of the general theory of relativity as applied to black holes, that if you try and keep on spinning up a black hole and have it in some sense all hold up together, there's a maximum rate of rotation that is possible. And if you could imagine doing the same thing on the Earth, you could imagine some alien invader sticking ropes on the surface of the Earth and making it spin up and spin up. And we know that if we span it up too fast, the centrifugal force will cause the surface of the Earth to fly off. The same sort of thing can be happening in a black hole, and for the somewhat similar reason, although one based in general relativity, there turns out to be a maximum spinning rate for a black hole. One of the things that the observations we have are showing us is that some of these systems do look like they are getting up close to that maximum limit, but none that we have seen so far have exhibited anything beyond it. So that's also a good vote of confidence for the general theory of relativity applied to these objects.
Okay, well, thank you. So, Mike, one of the interesting aspects of the event that was presented yesterday is that there seemed to be, confirmation that at least one of black holes, the initial black holes, was indeed rotating. Could you say a little more about that? And how do you find out, such property?
Yeah, so that was one of the interesting aspects of this second detection. So we have the first detection on September 14th, 2015, and that was a very loud event in which the only thing we were able to say about the spins of these objects was that of the constituent objects, the mass 1 and mass 2 before they coalesced, was that one was not maximally spinning. So the dimensionless spin from 0 to 1 was less than 0.7 for one object. That's not very well constrained, and it's all of this information is extracted from the waveform that lands and registers in the Hanford detector and the Livingston detector. You extract this through templates, general relativistic templates, and numerical relativity ultimately. And we can talk more about that if you like. But so in that case, we could only say not maximally spinning. The resultant larger black hole that forms after the merger, it's spinning, but you expect that from the angular momentum of the two objects. And then the second event, the Boxing Day event, the waveform was such that when we extracted the spins, the dimensionless spins, we could see that at least one object was spinning with a dimensionless spin of 0.2. So it's a greater than 0.2. So it's a case where we understand that the component black hole has spin rather than just the one that results from the merger. So again, we're getting this solely out of the waveform. That's the only information we have is the gravitational waveform that is extracted from the modulations in the detectors. We wondered then if we wouldn't see evidence of precession of the orbital of the plane of the orbit of the system, but the signal to noise in this, the combined signal to noise in the two detectors was 13, and wasn't sufficient to extract any information on precession if it was there.
So to be precise, 0.2 means that it's 0.2 times the maximal spin, or 20% of the maximal spin.
That's right.
Okay, so we still on black holes and rotating black holes. We have a specific question coming from Stephanie, addressed to you, Roger. Dr. Blanford, could you explain the jets at the poles of the black holes? Have we learned anything recently about what causes them? Okay, you certainly have the expert on the question in the room. So that's a great question. Okay.
So hi, Stephanie, and thank you very much for the question. I love to talk about this. I think the answer to your question is, can we fully explain the jets? The answer is no, but we have learned an awful lot in recent years, and a picture is emerging, some parts of which I think are now very well substantiated by observations, and I have to say just as much by simulations as well, the sort that my colleague Tom Abel discussed, and other parts of which are in the form of, if you like, conjectures, which we have some optimism will be tested by observations over the next 5 to 10 years. So there's a lot of excitement in this field. For those who don't quite understand the context of the question, I should say that many massive black holes in the nuclei of galaxies create anti-parallel jets that seem to squirt out from the region around the black holes, and material seems to move with speed very close to the speed of light. So this is a remarkable phenomenon, and for 50 years we have tried to understand how nature pulls off this trick. What seems to be going on is that there is a disk of gas that orbits the black hole, probably in the same sense as the spin of the black hole, and trapped by this disk of gas is magnetic field, the same sort of magnetic field one associates with the Earth. And this magnetic field, in a way that I just alluded to in the previous in one of the previous questions, is able to grab hold of the black hole and extract some of the spin energy that resides in its rotation. This in turn makes large electrical fields, large voltages if you like, and so it's acting a little bit like a giant battery. And so this is the source of power for the jets, and it's not surprising that if we do things with electric fields and magnetic fields in this rather evacuated region, after all, a black hole is rather good at getting rid of all the gas around it, if we do things in this way around this evacuated region, that things are going to fly off at the speed of light, and that's what we think is happening. The one more ingredient of an explanation that I will just mention here is that magnetic fields have two rather special properties. One is they have a sort of pressure with them, which causes them to push out in all directions. But more important for this application, they also have a tension associated with them, so they act a little bit like rubber bands. And so when you have these magnetic fields near black holes and accretion disks, and you spin them around, then the black holes, the magnetic field, associated with those black holes will be wrapped around the outflowing jets of plasma, and the tension in those magnetic fields will lead to it being focused and collimated. So that in words, and I wish I had some pictures in front of me, that in words is the start of an explanation for how these jets are created by black holes spinning and the accretion disks that orbit around them. So thank you, Stephanie, again for your question.
Yeah, thank you on my part. Tom, precisely, I've seen some spectacular simulation of, the way that these jets are, coming from this lab. So could you say a little more, what simulation, what is the role of simulation in this, understanding this process?
Yeah, I mean, you're exactly in that situation where we're trying things out. So for a black hole, we have sort of an understanding of the space-time, what it might look like. And now to understand these questions, is really think through what happens if we put some gas in there that is going around it. Now the gas will have all sorts of forces on itself. It's pressure forces. The hotter regions, hotter and denser regions will push on the lower density ones. And we'll have friction in the gas as well. Now we already talked about magnetic fields being dragged along. So all those processes, what we're trying to capture in these calculations as gas moves around in these space-time. So we still have to do a number of simplifications at the moment. Ideally, in an ideal world, we would follow every electron and proton and every individual constituents with it and the current it makes and the magnetic field it generates. But unfortunately, our computers do not allow us to store all that information. And so we use some more simplified models of how a fluid generically behaves. And but certainly calculations that Raj in particular with collaborators had carried out and we visualized for some of the movies we can show you is that a lot of qualitative effects are actually already there in these sort of simplified models where for how we think about the fluid. And specifically, these jets, you can study of how they stay collimated and how they accelerate, how material gets flung out from the inner parts of the disk going around the black hole. It becomes part of the jet and then gets accelerated to these very high speeds going away from it. The thing we would love to do is do these calculations now, but also follow millions and trillion times further distances away from the black hole. Can we explain that just because we accelerated near the black hole, that they still can be going when they're a million light years away, which is the remarkable observations we've had for a very long time. And there, similarly, we do need to do quite a bit more work algorithmically and how we design these calculations in order to capture all these scales and see whether our starts of an explanation, I think Roger just called it, really hold true and can explain the entire phenomenon.
Mm-hmm. Okay, so great view on how to understand something which is indeed what happens with astrophysical black holes, as I was saying. Okay, a question from Gary, and I guess that's for Mike. Because emerging black holes had less mass compared with the first discovery, will the second discovery help to better detect similar events in the future? And does this latest discovery suggest that there could be more black hole mergers than previously expected? So if I understand clearly, it's more like now that you have at least 2 events, maybe you could talk about the trigger that also was mentioned in the press conference yesterday. Can you start making predictions about what we call physicists call the rates, so a number of events that you expect?
Yeah, sure. That's a nice question. So we have two candidates. The first, or sort of the two confirmed detections. The first event was a pair of black holes that were really quite massive, more massive than were seen in X-ray binary EM observations. So these masses were about 36 and 29 solar masses. It's been revised a little bit since the detection. And in the Boxing Day event, the constituent masses were 14 solar masses and 8 solar masses. And so that's a much lighter pair of black holes. That means they chirp up to a higher frequency range when they coalesce and merge into a larger black hole. And so the lighter systems then sweep across the sensitive band of the LIGO detector. The sensitive band of a LIGO detector is nominally sort of 10 hertz at the low frequency. We're not quite there yet. And this is in the frequency at which the arms are modulated. So 10 cycles per second or 10 hertz, up to intermediate bands of 100 cycles per second, 100 hertz, and then at the high end upwards of a few kilohertz. And this matches up with the audio band. It's why we can play the waveforms and you can hear it on a speaker. So whereas the heavy system, the original detection, coalesced at about 350 hertz, this second detection coalesced at higher frequencies, several hundreds of hertz, on the order of 600 hertz, and that meant it spent a full second in the gravitational wave band of LIGO, whereas the first one was only 0.2 seconds. So they're different animals, they're different systems, and that is telling us something about the population of binary black holes that we're sensitive to. So we made a rate estimate just based on the first event. That's tough to do with one event, of course. We also had the trigger that you mentioned, which is an intermediate sort of system. It's 13 solar masses and 23 solar masses. And so we've revised that now with a third event to fold in, with this Boxing Day confirmed event folded in. We find a binary black hole rate of 9 to 240 mergers per cubic gigaparsec per year. So what does that mean? If you have a volume, a gigaparsec in radius, and you ran for a year, you would find something like 9 to 240 of these events. And so these systems then are perhaps a little more, they occur more commonly than you might have expected. There was rate estimates before advanced LIGO started running, which included 0. So 0 was a real number. Some theorists suppose that there were no mergers in the lifetime of the universe. That's off the table now. We know it's something like roughly 9 or more per cubic gigaparsec per year. That rate will become more and more better understood as we go into our future observation runs. We accumulate more events. The error bar on that number, we'll just measure it and it'll get smaller and smaller.
Tom, do you want to comment?
Oh yeah, I mean, for the rates, it's it's closely connected again with the types of calculations we can do. But if you try to imagine, you're going to predict signals here that can come from billions of light years away, and now you have to think about all the possible sources that exist in this entire volume, and then make sure that each of them you understand at great accuracy in order to be able to sort of sum up the total signal that you get. And so I think it's great that we now have the observations, because clearly we couldn't do the calculations at that level of accuracy. And from a petty example that I already mentioned at the beginning, with the very first stars, we're really excited about having massive stars, some of them making binaries. All we knew is that yes, we should have massive star binaries quite early on. But that was 13.7 billion years ago that they were made. Now, in order to turn that into a prediction of what LIGO should see, we should have real confidence about all the events that happen as this binary evolves. And there's many interesting things that stars can do, particularly massive stars shed off some of the mass of the outer envelope. They can interact with other bodies around. At exactly what distance are they born? And so we always, we certainly tried, and have a good sort of record of working out some of the effects and enumerating all the aspects. But really going through the calculation and then have the high accuracy at the end of how many events exactly you're going to have, we just cannot have. There's not enough certainty about many individual aspects of these processes we need to consider. So to have the measurement, so much better.
So we have quite a few questions about other sources, because as Roger mentioned at the beginning, one was expecting more like neutron star binaries. So I think I remember yesterday in the press conference there was a question asking, okay, what about the other sources? Are you still looking for them? So Mike, are you still looking for these other sources? And so Roger mentioned neutron star binaries, but there is a question by Brian about gamma ray burst as well. So can you tell us about the other sources?
Yeah, absolutely. So we're of course still looking. We're continuing to analyze the initial advanced LIGO run for other types of sources, and those include binary coalescences, not just of black holes, but pairs of neutron stars, or perhaps one of each, a neutron star and a black hole. And these latter two systems should have an electromagnetic counterpart associated with them. And they may be, in fact, the short GRBs, short gamma ray burst events that people, X-ray and gamma ray astronomers know and love, and some of the most energetic events that are going off and we record every few days in the universe. So there may be a coincident, at some point there will be, but it's hard to say when, a coincident detection in Earth-based gravitational wave detectors for a binary neutron star system, or a black hole in a neutron star, and a gamma ray burst, and that would be extraordinary multi-messenger astronomy. So we're searching for those. We certainly did, like Roger suggested, expected to see, if we saw anything in the first run, to see a binary neutron star system. We were surprised on September 14th to wake up to a binary black hole. But we do search for other objects. Individual isolated neutron stars in our own galaxy, whirring away as they rotate on their axis. If they have some sort of mountain, where here a mountain is sort of like a hemispherical lobe on the side, they could give off a weak gravitational wave whisper, which would be in your detector for sort of the lifetime of the experiment. That turns out to be a tough search because the signal's weak, because it's not, if you think of the nature of two black holes or two neutron stars revolving around each other, you can see the sort of dumbbell-like nature that gives off gravitational waves. Here you've got something that's very nearly spherical, maybe some deformation on the side, which would give off a weak gravitational wave, plus they would be spinning down, and that signal, it would be Doppler modulated due to the relative motion of our detectors and that star. And so that makes for a very difficult search, but people do that search through primarily through the Einstein at Home distributed computing system. People can download some of our data and analyze it on their home computer in a screensaver package. Another type of source is burst sources from things like supernova, or perhaps more exotic things like cosmic strings. And then there is a possibility of a sort of noise background, a so-called stochastic noise background, which is unlikely to be a relic from the early universe. That LISA or pulsar timing arrays, or experiments that look for the polarization in the cosmic microwave background, like BICEP, they're more likely to see this. But that's a possibility if there's something exotic going on in the early universe for LIGO. What would be more likely is this population of binary black holes gives a source from a more recent time which you sum up and will give a noisy background, which is ultimately gravitational waves. That's a possibility for LIGO to see in the future.
Since you mentioned LISA, and since I see that Stefano is still with us, maybe you can say a few words about LISA sources, Stefano. Of course, binary black holes, but what else could LISA detect?
Well, you realize I'm a plumber, right? So it's a bit out of my. But I mean the two or three main sources for LISA. One is binary black holes, but these are the big black holes, 100,000, 1 million, 10 million times the mass of the sun. They cannot come close, right? So they are slow and emit waves in the milliards frequency range. These are such intense signals that they should be visible basically a few hundred million years after the Big Bang, visible with a signal-to-noise ratio that can go up to a few thousand, and so allows to do precision gravitational wave physics and precision, I would say, general relativity physics. There is another famous source, famous among us, source for LISA, which is the fall of a small black hole, say stellar mass black hole, into a big black hole. Then these objects are calculated to go around the big black hole for 100,000 orbits, and while they orbit the edge of the event horizon, they basically send a signal which is like doing the geodesy of a black hole. It's like there's missions that map the gravitational field of the Earth, but done at the edge of a black hole. And then obviously there are other sources like just more ordinary compact binaries in the galaxy. The most relevant thing is that this is a high precision gravitational wave physics, because the signals are so intense that you can really measure parameters and check hypotheses, including the no-hair theorem of general relativity, to very high accuracy. So it's a very high accuracy laboratory, and it's a very deep field observatory. It really, I mean, those sources are so intense. People calculate that a supermassive black hole collapse emit more energy in gravitational waves than the total energy emitted by the universe in the form of electromagnetic radiation during the same time. I don't know how accurate is that, but certainly fix a scale on how intense are these phenomena.
Okay, thank you. So we have been on the air a little more than an hour. There are still many interesting questions, so we can't get all of them. Let me just come back for a second to Roger. And the binary systems of neutron stars. What kind of science would you learn if from detecting these effects with gravitational waves?
Well, just to say, this is a type of system that we know exists because radio astronomers have for a long time seen radio pulsars, which are spinning magnetized neutron stars, and they have found examples of them where they're in binary orbits. And so they're in binary orbits, they're quite a distance apart at the moment, but they're radiating gravitational waves, and we know that in 100 million years or thereabouts they will be prime LIGO sources. But we're rather impatient. We want to see them sooner. So what we're looking at is other examples of those that are much closer to merging and coalescence. And by looking at these binary pulsars and showing that their rate of shrinkage is just what is predicted by the general theory of relativity, we can make a pretty good estimate of the rate of events that LIGO ought to see. And so there's a lot of optimism that eventually LIGO will see these. Now, when it does see these, as was emphasized, you can learn quite a lot, not just about the general theory of relativity, but also about the behavior of the nuclear matter that it comprises a neutron star. A neutron star we can think of as a giant atomic nucleus with 10 to the 57 nuclei in it, and by making those two neutron stars come together, you of course deform them and distort them, and you learn a lot about nuclear physics. So that's one piece of new physics you'll learn from this. The second piece of new physics that I think you will learn is through the electromagnetic, or indeed even possibly neutrino signals that will be seen using multi-messenger astronomy in coordination with the LIGO detections. And those will tell us what happens to the material that escapes the clutches of the newly formed black hole, how it behaves, how it radiates, how it makes gamma rays and radio waves and optical waves, and as I said, possibly even neutrinos. And we're going to have a lot of fun finding that out, and my colleague Tom and his fellow simulators are going to have a real challenge to try and simulate this and understand the more detailed physics of what is going on.
Okay, well, thank you. Last question from Ibrahim. That's for you, Roger. Can we generate energy from the gravitational waves for spaceships, for example?
I don't know any way of doing that in a useful way, certainly not for spaceships, but if anybody listening has a good idea, I'd certainly be pleased to hear of it. But I think it's I'd just say something slightly more serious, is that for a long while in the history of this business, there was a lot of confusion amongst theoretical physicists as to whether or not there was proper energy associated with gravitational radiation. And some very famous people, including Albert Einstein, got somewhat confused about this. I think it's fair to say that we've now sorted that out. We have a very good description and a very good way of associating energy with gravitational radiation, and what our colleagues in LIGO have demonstrated very, very clearly is that energy gets from the merging black holes to the detectors that we see in Washington and Louisiana. So we have a clear experimental demonstration of the transport of energy by gravitational waves, and theoretically I think we now understand that pretty well.
Okay, well, thank you very much. Well, congratulations to LISAPathfinder, congratulations to LIGO and Virgo, and thanks to all of you. I think it has been another great hangout. As you see that news are coming almost every day or every week, so we hopefully will have plenty of other news from LIGO Virgo, probably from LISAPathfinder as well. We'll have to wait a little more for LISA. But the exploration of the gravitational universe has just started. Okay, so my apologies. I selected many more questions, but we could not get through all of them. So we'll try to get to some of them by writing on the course platform. Apologies for those who could not get a direct answer from our guests. Well, thanks a lot to KIPAC. This was great to organize the one hangout from here. Thanks to Mandeep as well, who helped me co-organizing this event that went very smoothly. Okay, hopefully we might organize another one. When there's a big event like what happened in the recent days. Okay. Thanks to everyone, and of course the course is not finished. We can still and will be still answering questions on the course platform. Okay, bye for now. Bye, Mike. Bye, Stefan.
Thank you.
Bye bye.